How does decoherence impact basic quantum circuit building? Imagine trying to keep a delicate soap bubble floating in the wind. That's similar to how quantum bits, or qubits, need to stay in their special quantum states. But in real life, the environment is like the wind, constantly trying to pop that bubble. This is what we call decoherence. It's the process where a quantum system loses its quantum properties because it interacts with its surroundings. When this happens, the qubits can no longer hold their superpositions or stay entangled, which are the key features that make quantum circuits powerful. In building simple quantum circuits, decoherence is a big challenge. Quantum circuits relying on qubits being in multiple states at once, which is called superposition. When decoherence occurs, it causes the qubits to lose this superposition by mixing with the environment. This means the quantum information stored in the circuit gets destroyed or becomes unreliable. As a result, the output of the circuit can become incorrect or unpredictable. Another effect of decoherence is that it limits how long a qubit can stay in its quantum state. This is known as the coherence time. If the circuit takes longer than this time, the qubits will lose their quantum properties before the computation finishes. This makes it hard to perform complex calculations that need many steps or gates. The longer the circuit, the more chances decoherence has to interfere, which reduces the accuracy of the results. Every time a quantum gate is applied, decoherence can cause errors. These errors happen because the process of manipulating qubits introduces more opportunities for environmental noise to affect them. Different types of decoherence, like amplitude damping, which is energy loss, and phase damping, which is the loss of phase information, both make the gates less reliable. This reduces the overall fidelity or correctness of the quantum circuit. Environmental noise is a major cause of decoherence. Things like temperature fluctuations, electromagnetic interference, and vibrations can disturb the qubits. For example, superconducting qubits need very cold temperatures to work well, but even tiny vibrations can cause decoherence. Trapped ions and solid-state qubits face their own environmental challenges, which makes designing and operating quantum circuits more complex. To fight decoherence, researchers use several strategies. Quantum error correction involves encoding information across multiple qubits so errors can be detected and fixed. Dynamical decoupling uses sequences of control pulses to cancel environmental noise. Decoherence-free subspaces are special states or groups of states that are less affected by noise. Also, circuit design focuses on reducing the number of gates and overall circuit depth to limit exposure to decoherence. In the end, decoherence sets fundamental limits on building reliable quantum circuits. It restricts how long qubits can keep their quantum states and how accurately gates can operate. Overcoming these effects is essential for creating scalable and dependable quantum technology. That is why a lot of effort goes into improving coherence times, developing error correction methods, and finding ways to reduce environmental noise.